In the previous topic, we've seen how atomic orbitals combine to give a molecular orbit. But if we look at the picture of atomic orbitals of carbon, we'll notice a slight inconsistency. Carbon, as we know, has 1s orbitals, which are completely filled, then a 2s orbital, which is filled as well, and then 3 2p orbitals, 2 of which are filled with 1 electron each. According to this picture, carbon should form only 2 bonds. Because there are just 2 unpaired electrons that can engage into binding with other elements. However, what we know from a vast majority of carbon compounds is that carbon indeed forms 4 bonds. An additional puzzling effect is that these 2p orbitals are at a 90-degree angle. But in most of its compounds, for example methane, carbon doesn't have a 90-degree angle. Instead, in this compound, where a centrally bound carbon atom is bound to 4 hydrogens, an angle between individual CH bonds is 109 degrees and 28 minutes. The question is, first, why does carbon form 4 bonds? And why is this angle such a strange value? In order to explain this, a concept known as hybridization was introduced. Hybridization is a notion that in order to achieve experimentally observed binding in methane, carbon orbitals recombine within itself. So we have a 2s carbon orbital with 2 electrons and the 3 2p orbitals with 1 electron in 2 of them. A process of hybridization will form something that's a hybrid between these 4. Indeed, it will form 4 orbitals which are all same in energy now. So they're equal in energy. And since they're all same in energy and we have a total of 4 electrons, each one of them will have only 1 electron. And this now explains how carbon can form 4 bonds. Since these orbitals are originated from 1s and 3p orbitals, their name is Sp2 orbitals. And they're equal in energy, as I mentioned, but they're also oriented at exactly 109 degrees and 28 minutes relative to each other. Why is this angle so special? The reason that this exact angle is observed in methane and other compounds is that it's an angle of internal tetrahedron. So tetrahedron is a platonic solid which looks sort of like this. And tetrahedral structures allow the maximum possible separation in 3-dimensional space of 4 electron pairs, right? And so this specific structure allows maximum separation. And if you think, why is maximum separation of electron pairs favorable? It's because electron pairs are all negatively charged, and so maximal separation means also a minimal repulsion of these same electron pairs. Okay, well, this would be the so-called Sp2 hybridization, but there are also other types of hybridization which explain binding in other carbon molecules. For example, a molecule of ethene that we've seen already a couple of times in this course has an internal angle of about 120 degrees. And this angle is 120 degrees as well. This concept is explained by the so-called Sp2 hybridization. Now, what does Sp2 hybridization mean? Well, it means simply that we have, starting from 2s and 3 2p orbitals, we're going to combine the s orbital with only 2 of the p orbitals. So we'll have 3 of them, and these are now the Sp2 orbitals, while one of the p orbitals is left by itself, and this is still a 2p orbital. These orbitals are very close in energy, and so that's why Hund's rule applies to all four of them. Again, the question is, well, why 120 degrees? It turns out this is the maximum separation for situations when we have 3 electron pairs. Now, these orbitals, when combined, start with 2s and 2p orbitals, and we're going to get 3 orbitals which are oriented at 120 degrees to each other. So they look kind of like this. Now the question is, what happens with that 1p orbital which is left standing without the hybridization? Well, the p orbital engages into a pi bond. In other words, on each of the carbon atoms we have the sp2 orbitals forming the sigma bond, but then we have this lateral overlap of 2p orbitals, which forms the pi bond. And that's why in ethene we have a double bond, one of which is sigma and one of which is a pi bond. There is yet another type of hybridization that we should talk about, and this hybridization is observed in acetylene, for example. A very simple molecule, and here we have a 180 degree angle which corresponds to so-called Sp hybridization. Now you can already anticipate that Sp simply combines 1p and 1s orbital to give us 2 orbitals oriented at the 180 degree angle, and also that the 180 degree angle is then a maximum separation angle for situations when you have only two electron pairs. Again, the question is, well, what happens to the p orbitals? There are 2 p orbitals left on each carbon now. So that's 2 p orbitals left, which now engage laterally into 2 pi bonds with p orbitals on the other carbon. And so that's why we have this triple bond, where the first bond is a sigma bond, and both the third and the second bonds are pi bonds. Now, sp3 orbitals, the ones that we introduced first, are very common, but the problem with them is that they're tetrahedral, right? And that means they're not planar. And since most of our chemistry representations are really being described under a plane of a board, or on a screen, or a paper, there's a bit of a problem in projecting this three-dimensional tetrahedral structure onto the plane of the paper. And that's why the following convention was introduced to assist us in that. For example, if you look at the molecule of methane, we will draw up that molecule this way. There we have 4 bonds, and 2 of them will be simple normal bonds. One of them would be this thickened wedge, and this implies that bond is in front of the plane of paper or screen or whatever, whereas these little dashes imply that the bond is behind the plane. Now this convention, of course, this is a bit obvious. These bonds are in the plane. This convention now allows us to draw very complex molecules very quickly and with full appreciation of their structure. So we can draw things like this, where we know that this chlorine is in front of the plane and hydrogen is behind the plane. and here we can have a hydrogen in front of the plane and a metal group behind the plane. We can also say that this hydrogen is behind the plane, etc. And so we can draw a relatively complex structure with no ambiguity whatsoever. Now, to finally answer the question, how do we know what hybridization do we have in a certain molecule? How do we determine hybridization? We need to undergo a sequence of steps. The first one is to add up sigma bonds and free electron pairs on a given atom, because both sigma bonds and free electron pairs can occupy hybrid orbitals. The second question that we ask is, which hybridization would give you maximum separation? And we know that if we have 4 electron pair pairs, that would be Sp3. If we have 3, it would be Sp2. And if we have 2, it would be Sp. And then finally, the thing that we need to know is that in multiple bonds, first bond is sigma, second and third bond are both pi. Now, if you look at some examples of the application of this rule, they're relatively straightforward to follow. So if you look at ammonia, the structure of ammonia looks this way. And so here we have 4 bonds, proverbially speaking, because the electron pair is not a bond, and that means that this is an Sp3 hybridization. That also means that ammonia is going to take a tetrahedral shape. It looks sort of like this, and non-linear planar as I drew it here. If you look at the molecule of acetylene, here we'll have sigma, pi, and pi bonds, and this bond will be sigma. And so this is an Sp hybridization because we have only 2 bonds per carbon. Finally, if you look at a molecule known as Allene, which is a bit more interesting of an example, then what we'll notice here is that each of the peripheral carbons has 3 bond states, 2 to hydrogen and 1 to the central carbon, and so they're accordingly Sp2 hybridized. However, the central carbon has only 2 bonds to the 2 peripheral carbons, and it's Sp hybridized. And the bonds between them are formed by pi orbitals. And so if you look at here, this pi bond will be formed by orbitals in one plane, whereas this pi bond will be formed by orbitals in another plane. So Allene is sort of an interesting example where 2 different kinds of carbon hybridization are directly bound to each other.